Hey, welcome everyone. So today's topic is about this estimation of relative risk or rate ratio from a binary outcome. And well, as we do when our outcome is 0 or 1 binary outcome, the regression model we usually use is logistic regression, which produce odds ratio. And sometimes we want to show the result not in odds ratio, but using relative risk. And today's topic is how to do so. This is a topic of today. And if you have any question in the middle, please stop me. And these are the list of topic we covered up to now. Last year, we talked about multi-level modeling for using linear regression, logistic, and Poisson. And today's topic is somehow different. And then starting from next month, we start working on longitudinal model. And all the presentation slides, recording, and codes, they are located in this directory. And if you have any problem in accessing material, please let me know or let Octavio know. And well, this is today's topic, which I mentioned at the beginning. And I want to acknowledge Joanna and Marianela for providing me opportunity to work on this topic. And yeah. And the background. So logistic regression model is the first choice for a binary outcome. And logistic model is a commonly used model for binary outcome. And we don't have any other common models that assumes that outcome is binary. And well, logistic model provides result in odds ratio, which is given by this general formula, which is a ratio of odds in group 2 divided by odds in group 1. But we usually understand relative risk or odds ratio better, which is given by this equation, risk in group 2 divided by risk in group 1 in this simple formula. And then the common problem arises when the prevalence of observing the outcome is common. Why? The problem is we tend to interpret odds ratio as relative risk. And in fact, mathematically, always odds ratio is greater than relative risk when they are more than 1, and odds ratio is always smaller than relative risk when they are less than 1. But odds ratio and relative risk, they are similar when the prevalence of the outcome is rare. However, odds ratio is going to be much greater than relative risk, or odds ratio is much less than relative risk when the incidence or prevalence of the outcome is common. And people tend to use this cutoff of 10%. And this graph shows the relationship between relative risk and odds ratio at different prevalence of the outcome in the reference group. I changed my pen. So when the relative risk is 1, odds ratio is always 1 as well. However, let's look at when the relative risk is 0.5. Now the relative risk is 0.5, and when prevalence in the reference group is 0.5, meaning 50%. 50% and relative risk is 1.5, it means that another group has prevalence of 75% because it is 1.5 times 50% times 1.5, which is 75%. In this case, well, relative risk is 1.5, but odds ratio is going to be 3. So this is a kind of problem. Well, so when we get the result odds ratio of 3, sometimes we think that the risk is 3 times higher than the other, but it's not true. The odds is 3 times higher than the other group, as compared to the reference group. And similar thing is true to the relative risk, which is lower than 1. Say we take 0.5. Well, when the relative risk is 0.5, and then also we look at when the P0 is equals 0.5, or the prevalence of the outcome is 50% in the reference group. So the relative risk is 0.5. It means that comparison group has the prevalence of 25%. And in this case, in this scenario, relative risk is 0.5, but odds ratio is going to be 0.33. Okay, so the odds ratio is going to be lower as compared to relative risk. So this is a problem when we handle odds ratio when the prevalence is high. And when you look at this, prevalence, when the prevalence is 5% or 10%, it's very close to this red line, which is the identity line, or this is a line where relative risk and odds ratio are the same. And when we look at these two lines, they are somehow very close to this red line. So this won't be a problem. But when prevalence is high, the value of relative risk and odds ratio start departing. So what to do? So option 1 is we don't do anything. We report odds ratio, clearly stating that we are reporting odds ratio. Because the problem is some people, or including us, interpret odds ratio as if they are odds ratio. So nothing wrong with the logistic model, but the problem is us. So we report odds ratio. But sometimes we may prefer to report the thing using relative risk. Or sometimes when you submit your result using odds ratio to the journal, they may tell you that, hey, your prevalence is kind of big. So why don't you present the result using relative risk? And in this case, we have to think about how to present the result using relative risk. And how to do so? These are 3 major methods to do. 1, we use log normal regression. 2nd, we use Poisson regression combined with robust variance estimation. And last method is to use marginal standardization. And we go through much more in detail about these 3 methods. And today also we are going to use sample data, which is a simulated data based on cerebral data from Brazilian National Health Survey, which is PNS 2013 among adult population. And as I mentioned, well, it's a simulated data. This is different from original data set. So keep in your mind, I simulated to protect the confidentiality. And the sample size is big, almost for 32,000 individuals, and the data set contains these variables. By the way, the data set is in the folder I mentioned in the Google Drive. And study aim is to assess association between poor health and age by sex. Association between poor health and age by sex, accounting for clustering of data in Brazil 2013. And actually, the overall prevalence of poor health is 32%. So it's very common overall. And this is a crude association we observed. So on the y-axis, we have prevalence of poor health on a logit scale. And the horizontal axis, we have age as a continuous variable. So we do use this plot when we want to fit logistic model. Logistic model, if you can imagine the left-hand side of the observation, it's logit of probability of poor health. So we have to take this preference on logit scale to see if age can be included as a linear term. Well, when we look at the association between this prevalence of poor health and age for male, well, kind of linear. And for female, it's not linear, but we see a curve. Okay, so this implies that we cannot include age as a continuous variable. And well, if we are going to use Poisson or log binomial model, the left-hand side of the equation is a log of probability or log of prevalence. So we have to see the association between log of prevalence versus age. So this one, the scale is the prevalence the prevalence on log scale. And now male population, also the association is now not linear, but we see some kind of curve, and female like this. So now we are going to compare different models, and it doesn't seem reasonable to add age as a continuous variable. So we decide to use age, we decide to include age as a categorical variable because we don't have to assume linearity assumption. Then, well, for the demonstration purpose, first of all, I fit the logistic model. And this is an equation for when we use a mixed effect model. And this is an equation when we use GEE model, which I touched a little bit last year. So the equation is logit of probability of outcome is equal to 1. What does it mean? Well, Y and J is a self-rated health. Poor health is coded as 1, and good health is coded as 0 of the J's person in the city I, or I city. Okay. And this is the equation, and this logit of this probability is given by random intercept, which varies depending on in which city you live. And we have the term for age, the term for sex, and the term for the interaction term between age and sex. Some of you may get confused because it says X beta instead of beta X. Well, I use this notation because we have multiple levels of age category, and I didn't just want to write beta 1, age 1, beta 2, age 2, beta 3, age 3, and so on. So just to make everything 1, I use this notation using matrix form. And this one, random intercept, we assume that it follows normal distribution with global mean, which is beta naught, with certain variance. And well, we are not going much in detail about these numbers, but we just want to make sure that we fit the right model. This is a mixed effect model, and group variable or clustering is at city ID, and we are calculating odds ratio here. And for GE model, so instead of, for GE model, we don't have random intercept, but we have only global mean. And apart from that, the equation is the same. And this is a result. And we fit the right model, GE, and clustering at city. And we use a link function, which is logit, this one. And family binomial, meaning outcome is assumed to be 0 or 1. And we use a working correlation of exchangeable. And we get odds ratio. And we covered this topic a little bit, but usually always the odds ratio given by GE model is smaller than odds ratio we get from mixed effect model. And then, but now, well, previously these were given by odds ratio, but we want to present in relative risk. And then the topic is what to do. So option 1 is log binomial model. How to do so? We fit the model, specifying the outcome is binary, meaning 0 or 1. By specifying this, the variance will be calculated based on this assumption. And we use a log link function. So actually, when we look at this one, when we compare log binomial model and previous logistic model, this is a difference. Here, previously we had logit here, but instead we use log. By doing this, the exponentiated coefficient is going to be now relative risk, not odds ratio. But the problem of this log binomial model is we face this problem, convergence problem. And log binomial model may work in simple equation, but when we have many covariates, or depending on the level of clustering, we face this problem, convergence. This is an example of log binomial regression. By the way, log binomial mixed effect model, we cannot fit this model. I think because of mathematical reasons, this is not an option at least when we use SAS and Stata. And we have only one option with log binomial for multi-level regression. If you don't use a multi-level, when we don't have clustering problem, sorry, you forget about what I was going to say. So when we have multi-level data, we have only this option, GE model. And we just make sure that we use a model correctly. What this is GE group at city level, and we use a log link function. So this log coincide with this one. And family binomial, meaning we assume that outcome is binary 0 or 1, and we use an exchangeable correlation structure. And here, although here we see exponentiated B, but this one is now relative risk, not odds ratio. And in this case, we didn't have any problem in convergence, but sometimes we do. And next option is this one, Poisson model with robust variance. So what do? So we fit Poisson model or generalized linear model, GLM, with a Poisson outcome with a log link function, but we couple with robust variance estimation. So this equation is exactly the same as when we talk about log binomial regression actually. But the difference is here, previously, we assumed that this Y takes only binary outcome 0, 1, but now we are using Poisson model. So we are assuming that Y takes integers starting from 0, 0, 1, 2, 3, 4, and continues. Uriel, yes. Oh, I see you. You're raising your hand.
Yeah, I had a quick comment about the log binomial model,
Uh-huh.
which, as you have said, has an additional problem that the link function, the logarithm link function, maps to the positive real numbers. So if you predict a value with this model, it might not necessarily lie into the 0, 1 interval.
Yeah, thank you. And it seems that I saw this report from different literature, but it seems that as far as it seems that it's not a problem in case of log binomial, it seems, and having these covariate in the model, it doesn't seem to go beyond one. This is what I read, but I will touch on this topic later. But thank you, Riel, for your contribution.
Yeah, it usually depends on the values of the predictor. It might not go off the 0, 1 interval, but in general it does, because the x beta vector, the linear predictor, maps to the real numbers. So when you inverse it, it's going to be the exponential of something that maps to the real numbers. So it's going to map into the positive real numbers, not necessarily to 0, 1.
Yeah. Thank you.
And you also have a problem with the Poisson model, because the Poisson distribution is assumed to lie into the positive integers interval, so 0, 1, 2. And when you use a Poisson model with robust variance, you're assuming that the outcome can only take values that are close, that are exactly, 0 or 1. So if the linear predictor lies close to 0 or 1, the probability mass is going to be concentrated in these values, but then again, it might not be. So your standard errors and some of the estimates might be inconsistent with this model.
Thanks, Leo. So, well, actually, that is something I was going to talk. And
Sorry.
no problem at all. No problem at all. So we are using Poisson model. And so here we assume, although our outcome is 0 or 1, but we are fitting a model which allows not only 0 and 1, but also others, meaning 2, 3, 4, 5, and so on. So there's a problem here. And at least this variance is going to be different, because variance structure is that variance depends on the assumption we make about the distribution of outcome. So because of it, we need to couple with this robust variance estimation so that we can fix misspecification of the variance. But the problem is, this is what Uriel said, we can obtain out of range predicted value. In other words, we can get predicted probability which is more than 1, which is not possible. And this is a result we get from by fitting this model. Well, if it's a right regression, well, this is a result from mixed effect Poisson model, and this is GE Poisson model. And both of them calculate a relative risk or risk ratio, but the standard error is based on robust standard error, not usual standard error. And if we don't use variance estimation, robust variance estimation, your inference or confidence interval and p-value are going to be wrong. So you make sure that you include this robust variance estimation when you model. And also a little bit, as I mentioned previously, GE estimate was a relative risk estimated from using GE model is somehow smaller as compared to those we received from mixed effect model, but it's not that much in case of Poisson model. And well, this one come to what Uriel mentioned. So why we use logistic regression? Why logistic regression is good for binary outcome? And one reason is as follows. So this is the equation for Poisson log binomial model. Log of probability is given by linear combination of coefficient and observed value. And logistic regression, we have logit of P, which is given by this. Logit of P meaning log of P divided by 1 minus P, connected with linear combination of coefficient and observed value. And this one, log of P, it's bounded by 0. So here, this is the probability of P starting from 0 to 1. And here I plotted the association between probability and log of P. And as you can see, lower bound, it goes to negative infinity, but upper bound, it's up to 0. It cannot take, this log of P cannot be more than 0. However, this part can go beyond 0. And if we get beyond 0, it means that we are going to have probability more than 1. So this is a problem of having this link. And this is a problem for Poisson model, as I mentioned previously, and for log binomial model, according to some paper I read, it seems that predicted probability will not exceed 1 with given covariance. This is what I read, but you may want to check. And I have a reference for this, so please check if you have doubt on this. And for logistic regression, well, logit of P is bounded, probability is bounded between 0 and 1, but logit of P, it goes from negative infinity to positive infinity. And this linear combination part, this right-hand side of the equation ranges also negative infinity to positive infinity. So here, we don't have a problem of having predicted probability exceeding 1. So this is one reason why we want to stick with logistic regression instead of thinking about as a model. So mathematically, it's more convenient. But do you want to present some data using odds ratio or relative risk? This is a judgment we have to make. And to solve this problem, there is another way to calculate relative risk, which is called marginal standardization. And what we do is we fit logistic model. Okay. And then we calculate or we predict probability for each observations. And then we use this predicted probability to get average predicted probability. And then we calculate relative risk. And advantage of this method is we can calculate not only relative risk, but also risk difference as well. But there is, however. Well, the relative risk, I'm not sure it is called problem, but relative risk are obtained from predicted values, not from the model directly, because when we do regression model, well, we usually show the result using coefficient given by the model or linear combination of obtained coefficient. But in this case, we are based on predicted value and we start calculating relative risk and so on. So this is somehow different. So sometimes it's somehow difficult to explain the method, and also sometimes it's difficult to be understood correctly. And also, it may not be suitable if you want to present regression tables for included all the variables. Or it will be suitable when we have limited number of correlates of interest, like when we have only one or two exposure variable we are interested in. Maybe this is a way to go. This may be the way to go. And another limitation is software is limited to implement this method, marginal standardization, especially for especially after fitting mixed effect model or multi-level regression model. And this marginal standardization is easy to implement with this package Stata, but it's somehow complicated when you want to implement this using other languages. So this is another limitation. But there is advantage. This is suitable when the model includes interaction term in the model, or when you want to visually display your result. And what do I mean by that? I'm going to explain using the example. So first of all, this is a usual mixed effect logistic regression. Nothing new about this. But afterwards, we use this model to calculate probabilities for each observations. And then finally, we calculate the here prevalence for each category given by age and sex. So we have, well, in this example, we have 4 age category and we have 2 category for sex. So 4 times 2, we see 8 combination here. And how this was calculated, I go one step further. So first we calculate predicted probability where every observation was treated as if they were of the specific age and sex. What does it mean? So for example, first one, this one, 0.16, prevalence of 0.16. This is calculated as follows. So we have data set and we have age column and sex column. To calculate this, we get predicted probability by fixing age and sex, all of them, by fixing age at 20 to 29 for all the observations. And also by fixing sex as a male for all the observations. Some observations are male from the beginning, but some observations are for female. But we change everything. We change exposure variable all to female. And then we calculate predicted probabilities, and the average of this probability is here. So now you can see what I want to say. Somehow it's difficult to explain the method if you want to explain in detail. And if you have a question about it, you can go to this paper, Mueller's paper, which explains what I mentioned better, which you can find the difference at the end of this presentation. And well, so advantage of this marginal standardization is as follows. We can calculate not only ratio, but also we can predict probabilities. Sometimes it makes sense. Sometimes people can understand this better than just risk ratio. Right? So these are obtained prevalence for each age group for each sex. And this one may be very easy to digest, to understand, which cannot be done using other methods. And this is a summary of the results. So the first two, these are results using odds ratio, and these are results using relative risk. for male and female for each age category. And for each sex, age between 18 to 34 is a reference group. And as you can see here, for example, here, male age 65 plus, the odds ratio is 6.8, meaning the odds of poor health is 6.8 times higher as compared to youngest age group. But I said the odds is 6.8 times 5, 6.8 times higher. It's not a risk. Okay. And then let's look at this one. These numbers, they are shown in relative risk. So it's around 3.5 roughly. So when we want to present in relative risk, it's much smaller as compared to odds ratio. But here, this is odds ratio, this is relative risk. So we are using different scale. For this reason, we see different numbers. Also, this is a program some people mention. So you don't use odds ratio because it's going to be much higher than relative risk, and we tend to interpret odds ratio as relative risk. In this case, there is a great difference between odds ratio and relative risk. And just to review, for the value obtained from mixed effect model is somehow higher as compared to odds ratio, which is usually the case. And for Poisson model, this is from mixed model, and this is from GEE model, and these numbers are somehow larger as compared to GEE model, as we expected, because with GEE model, we calculate population average, the association we see amongst the population. And when we use mixed effect model, we are looking at what we observe in a specific city, which is usually higher. And this is a result from marginal standardization, which is similar to other estimation. And so we have 3 methods to use when we want to present the data using relative risk: log binomial, Poisson with robust variance estimation, and marginal standardization. So which one shall we use? This is a question. And you may want to try 3 of them as a sensitivity analysis, but finally you have to choose one. First of all, log binomial. We face this convergence problem very frequently. So in many cases, log binomial model may be maybe not an option in many cases. I did some analysis after I came to Drexel and Salubal, and usually this model didn't fit. So, and usually, but you can try. These 2 are the options, which is better, and it's going to be up to you and up to the scenario. The problem is this one, what Uriel mentioned. When we calculate predicted value, we are going to get probability which is more than 1. So which is not correct. But however, if our aim is to get a mean estimate, maybe it's not an issue because we are not using we are not trying to calculate predicted probability in this sense. And we can run this model without usually program for convergence. And relative risk estimation is based on regression coefficient. And regression table, we can present regression table as a usual other regression model. And confidence, the same thing for confidence interval, p-value, and any statistical package can handle this. So this is one good candidate. Only this one is a program, and if you feel uncomfortable about this, you may not want to use Poisson model. And marginal standardizations, I think a big program may be around here. So we calculate relative risk, confidence interval, p-value based on predicted probability, not from the estimated coefficient, which is different from other option. And also, this is very computationally somehow intensive process, and you may not want to create the table as you do for other regression model. Other regression model, you fit the model, you get a full table of regression, but in case of marginal standardization, we have to do one covariate by one covariate. So this is the reason why I said this is suitable when we are interested in only one or two exposure variable. And also, statistical packages somehow limited to run this method easily, but you can do so by writing programs. And another advantage of marginal standardization is when the model includes interaction terms, which is somehow difficult to present using usual table. And when we want to show the predicted rates, or in our case, predicted prevalence instead of prevalence ratio. So the summary is as follows. Logistic models are correct choice to handle binary outcomes, yes or yes. But when the prevalence or probability of the outcome is common, the odds ratio overestimates the risk ratio, or relative risk when odds ratio is more than 1 or relative risk is 1, and underestimate there's a typo when odds ratio is less than 1. And there are 3 options to obtain relative risk from a binary outcome. And we should choose one option out of these 3, depending on your needs, depending on your preference, and how suitable the models are. I think, and this is a difference. You can look at these difference when you want to know about the choice. Yeah, I think this is the end of this my presentation, and I wonder if you have any questions.
Thanks, Goro. No questions for here.
Hola, Tania. Sí.
Francisca parece.
Ok, entonces, Francisca.
Sí, si entiendo bien, dices que el modelo de regresión Poisson con varianza robusta, en el caso en que el objetivo no fuera predecir, estaría bien.
Generalmente.
Ya.
Pero adelante.
Sí, y uno podría calcular los valores predichos y de alguna manera asegurarse que al menos tengan sentido para decidir utilizar el modelo en el caso en particular.
¿Puede repetirme?
Si uno puede hacer las predicciones con el modelo Poisson y ve que estas van entre 0 y 1, ¿tiene más sentido usarlo?
Se puede. Bueno, yo contesté con una pausa. Because, well, if you finally, you're going to aggregate these predicted probabilities. When predicted probability for individual one, they may not be valid, but as a whole, maybe when you average them, maybe the effect of this having more than one probability may be small. But well, you can check about it. But at the same time, when I fit this model, Poisson with robust variance, actually this is what I do. And I compare with marginal standardization method as well, to make sure that Poisson model is good. Pero no sé si yo contesté apropiadamente, Francisca.
Gracias.
So es complicado. En ese sentido, mi preferencia. Ustedes tal vez tiene diferente preferencia, but my preference go with logistic model because we don't have to deal with this fitting model, and then we have to correct the assumption etc. But sometimes people say that we have to present with using relative risk instead of odds ratio. So sometimes we don't have option and we have to think what is the best way.
Pero la estandarización depende del valor que uno reemplace. O sea, de este valor promedio que uno ponga para hacer el cálculo, ¿no?
Disculpe, yo no entendí.
The standardization depends on the average value of the covariates that you will replace in the model.
Sure, and for marginal standardization, we fix only exposure of interest. Other covariates we don't touch. Only we change the value of exposure variable of interest. So if, for example, if we are interested in difference between male and female, we only modify this sex variable, but other variable, we keep them as they are when we do prediction.
Okay. Thank you.
You're welcome. Rosemary.
Hi, Goro. Hi, everybody. Thank you for your presentation. It was an excellent presentation and excellent explanation of the topic. I have a question with the mixed effect model, in this case, the Poisson models. When we have a mixed, for example, a multi-level model with a random intercept, we account the clustering of the level, for example, in this case, for the city level in the estimation of the variance.
Yep.
But in this case, we are adding a robust estimation of the variance. What are done exactly with the variance in this case when we use a robust estimation of the variance in a mixed effect model?
So we use this, we use robust variance because this is not for, this is not related with a random effect part, but this is related with, we are using Poisson model, which assumes that our outcome is 0 or above integer, but our outcome is 0 and 1 only. And we use this, how do you call it? We use this assumed distribution of the outcome to calculate variance. So when we use Poisson model, we are assuming that outcome is 0, 1, 2 or more, right? So here, and from this information, we calculate variance, which is wrong. So variance calculation is just wrong. For this reason, we use robust variance to correct this variance estimation. I wonder, did I answer to your question?
Yes,
Kind of.
but I don't remember if in this case it's a sandwich estimation of the variance. I don't remember.
Yep, it is.
Okay. Okay, thank you so much.
You're welcome. Fatima?
Yes. First of all, I want to congratulate you for bringing this discussion, which is really important because I see many people using odds ratio as a similar of relative risk. And it's important to show it's not the same. And usually what I do is odds ratio I'm using when I don't know the population and the risk, because to calculate the relative risk, you need to have the population at risk. And sometimes we don't have for some specific studies. And when you don't have, then you have to use the odds ratio. That's why odds ratio exists, to overcome these situations where you cannot calculate incidence, for instance, because you don't have the population at risk.
Yep.
So that's what usually I am using.
Odds ratio?
Odds ratio when you don't have the population at risk.
Yeah,
For
well, there's
instance,
no other option. Sure. Yeah, thank you, Fatima. Are there any questions, Tanya?
Yes, yes. When you said that you usually prefer logistic regression, are you saying that if you says the limitations and that it could be overestimate or underestimate the relative risk, it's okay, no? Or do you, when you have a higher prevalence, I mean.
I think I may just one line saying that we presented everything odds ratio, but in our case, prevalence is high. So I may state only one thing, but yeah, as I mentioned, fitting logistic model, nothing wrong about it. But the problem is we tend to think that odds ratios are relative risk, right? And in this example, we saw that the one age group had odds ratio of 6.5, something like that. But when we want to know, when we get this information in relative risk, it was 3 point something. So there is a big difference. In this sense, I just make an acknowledgement that I'm presenting the result in odds ratio instead of relative risk, and there is a so I may warn to the reader of your manuscript. But sometimes you may get reviewer saying that no, you have to show in relative risk, and you may not have option to insist that odds ratio is correct.
Okay, thank you.
You're welcome. Uriel, do you have any additional comments?
No, I think that you covered everything. It was, I think it was really nice to see the comparison that you did from the earlier slides and in the final slides, comparing the odds ratios with the relative risks. I think this is really interesting because we hear a lot about this, but having such a clear comparison done in a specific example is really instructive.
Thank you. And well, when you do your analysis, you may want to pick up one or two as a sensitivity analysis to make sure that what you're saying is not model dependent, but you can see similar result across regression model. And the UCARI family says that as a sensitivity analysis, I use this method and we receive very similar results, something like that in your method section.
Yeah, because in the end, actually, any type of regression model, if it's at least almost correctly specified, should give you an unbiased estimate of your regression coefficient. So this is a really good idea.
Thank you. Do you have any more questions? No. Okay. And if you get additional questions, please let me know. And so this is the end of today's session, and I think starting from next month, we start talking about longitudinal component. Previously, we are all based on cross-sectional data, but we have multiple level of clustering. But now we are moving to longitudinal model, so it means that we have clustered level, multiple clustered level like L2, L1, as well as we have longitudinal data starting from year X up to year Y, and we also want to model this longitudinal stuff. Okay, thank you very much everyone for joining this session, and we will see you next month.
Thank you. Bye-bye.
Thank you.
Thank you, Goro.
Thanks, everyone.
Bye.
Bye.
Thank you. Bye, Goro.
Bye.
Bye.